In 1912, in a recording studio in New York, a musician stood before a massive horn, holding a strange device with a metal bell and a diaphragm instead of a wooden violin body. The sound of this device was so powerful and focused that a primitive wax cylinder recorded it without a single distortion, while standard violins sounded muffled and illegible. Today, most of these mechanical instruments of the turn of the century are forgotten, although 100 years ago, they were the pinnacle of recording technology and home leisure. Number 8 on our list will surprise you, as it was assembled from ordinary wooden boxes by slaves who were forbidden from playing drums. And number 4 produces sounds resembling the laugh of a wild beast due to the friction of a wet cloth against a bamboo stick inside the body. Before we begin, be sure to subscribe to our channel. You will see that our ancestors were ingenious sound engineers who used the laws of friction, pressure, and resonance long before the advent of electronics. Let us begin our countdown of the 10 most amazing forgotten instruments. Number 10, the Stroh violin. This instrument, patented in 1899 by John Stroh, became the main symbol of the era of early mechanical recording. Instead of a wooden resonator body, the Stroh violin uses a circular metal diaphragm connected to the string bridge, and a long brass horn directed at the listener. The physics here is similar to a gramophone. String vibrations are transmitted to the diaphragm, which mechanically amplifies and directs the sound waves forward. The Stroh violin sounds much louder, sharper, and more focused than a conventional violin, which allowed microphones of the early 20th century to clearly capture the sound onto wax cylinders. Musicians valued this device for its unique telephone timbre and directional acoustics, which today are replicated using frequency filtering. Number 9. The slide whistle. This wind instrument, popular in American vaudeville shows and early jazz, consists of a metal or plastic tube with a piston inside. Unlike flutes with holes, the slide whistle does not have fixed notes. The musician blows into the mouthpiece and smoothly moves the piston along the tube. Physically, this changes the length of the air column inside the resonator, which shifts the standing wave frequency. The slide whistle produces a characteristic whistling sound with a continuous pitch slide, called a glissando, resembling cartoon sound effects or bird songs. For modern sound designers, this instrument is an example of a completely mechanical, manually controlled frequency generator. Number 8. The cajon. This percussion instrument, in the form of a wooden box, originated in Peru. In the 19th century, Spanish colonizers banned slaves from playing traditional African drums, so musicians began to use wooden boxes that had held fruit or fish. The physics of the cajon is surprisingly complex. The front panel, tapa, is made of thin plywood, and a circular sound hole is cut in the back panel. Metal strings are stretched inside the box close to the tapa. When striking the center, the low-frequency resonance of the box is excited, producing a bass kick drum effect, while striking the corners causes the strings to vibrate against the plywood, creating the characteristic rattling sound of a snare drum. The cajon became an ingenious example of combining two acoustic registers in a single wooden box. Number 7. The Hawaiian lap steel guitar. This instrument became the foundation of the Hawaiian music boom in the United States in the early 20th century. The guitar is placed horizontally on the lap, and the strings are tuned to an open chord. Instead of pressing the strings with fingers, the musician slides a heavy metal bar called a steel over them, holding it in their left hand. Physically, this eliminates the fixed division of the fretboard. The length of the vibrating part of the string changes continuously, which produces a soft, singing sound with a constant slide from note to note and deep mechanical vibrato. The lap steel guitar gave American country and blues their iconic crying timbre, which later led to the creation of the pedal steel guitar. Number 6. The steel pan. This instrument was created in the mid-20th century in Trinidad and Tobago from ordinary industrial oil drums. The bottom of the drum is bent inward, and individual convex sectors of different sizes are hammered onto the metal surface. Each sector is tuned by a blacksmith to a specific note. The sound physics of the steel pan is based on the mechanical isolation of vibration zones on a single metal sheet. When struck with a rubber mallet on a specific sector, only this area vibrates, emitting a bright, metallic, warm sound with many upper harmonics. The steel pan demonstrates how industrial waste can be turned into a complex, polyphonic instrument through precise distribution of metal elasticity. Number 5. The flexatone. This unusual percussion device, patented in the U.S. in 1924, consists of a flexible steel plate mounted in a wire frame with 2 wooden balls on springs. The musician holds the frame in their hand and shakes it, causing the balls to alternately strike the metal. With their thumb, the performer presses the free end of the steel plate to bend it. The physics of the process is based on changing the tension and curvature of the elastic plate when pressed, which instantly changes the resonant frequency of the metal. The flexatone emits a vibrating metallic whistle with a rapid pitch slide. Its unique cartoonish timbre was often used in classic animation and early jazz for comic effect. Number 4. The cuica, a Brazilian friction drum that became the heart of the samba rhythm. It consists of a metal cylinder with a stretched skin, but the main secret is hidden inside. A thin bamboo stick is tied to the center of the leather membrane. The musician holds the drum under their arm, reaches inside the body, and rubs the bamboo stick with a wet cloth while pressing the skin from the outside with a finger of the other hand. Physically, the friction of the cloth creates self-oscillations of the stick, which are transmitted to the membrane, causing it to vibrate. By changing the pressure of the finger on the membrane from the outside, the musician changes its tension and pitch. The cuica produces amazing talking and squeaking sounds resembling the laughter or cry of a monkey. Number 3. The organette. This mechanical reed instrument was extremely popular in American homes in the late 19th century. It worked by turning a handle, which simultaneously operated bellows to supply air and pulled a perforated paper tape over metal reeds. Physically, this was the first home mechanical synthesizer. Holes in the paper opened the airflow to the desired reeds, extracting a melody. The organette allowed people to listen to complex orchestral arrangements without knowing how to play keyboards, laying the foundation for automatic players and the early concept of programming sound using punched cards. Number 2. The psaltery. This stringed instrument has a triangular wooden body over which metal strings are stretched. Each string is fixed so that its working part projects from the side of the body over an individual pin. The psaltery is played with a violin bow, drawing it between the pins. The acoustics of the psaltery are unique. Because the bow touches each string individually on an open section, the sound is crystal clear, without extraneous noise or clicking from finger presses. The psaltery sounds incredibly gentle, airy, and bell-like, resembling a glass organ with endless sustain, and is often used to create a fairy tale atmosphere in acoustic music. Number 1. The whirly tube. This simple acoustic device is a corrugated plastic tube that a musician spins over their head. The physics of this process is fascinating. Centrifugal force pushes air out of the tube, creating a low-pressure area at the handle and drawing air inside. Passing through the corrugated walls, the airflow breaks into vortices, generating self-oscillations. As the spinning speed increases, the sound jumps to higher harmonics of the natural scale. The tube emits clean, soaring tones, resembling an organ or a flute. This device clearly shows how ordinary aerodynamics and movement speed can produce pure musical resonance without the use of strings or membranes. Studying the physics of these 10 instruments proves that our ancestors knew how to use the smallest details of mechanics and aerodynamics to control sound. They created complex acoustic filters, resonators, and amplifiers, laying the foundation of modern sound production. Applying these principles allows the modern musician to go beyond the usual digital plugins and fill their compositions with live physical energy. If you were surprised by the physics of some instrument, be sure to write about it in the comments. Subscribe to the channel, give it a like, and may your internal frequency generator always sound on the most harmonious wave.